Now that we've got a good understanding of the life cycles of the stars, we can press on and begin to explore some of nature's largest and most majestic structures, galaxies. We're going to begin with our own Milky Way galaxy in this lecture, and then in our next lecture we'll be back to examine other galaxies and see how they compare. So what is a galaxy? Well, essentially it's an enormous assemblage of stars and gas and dust held together by gravity. What does our Milky Way look like? Well, these days it's rather difficult to see from our urban areas, but if you were to go out into the country on a beautiful, clear, dark night, you would see this faint band of light stretch across the sky. That really doesn't tell us the whole story by any means, because we are actually inside of our Milky Way, and therefore it's difficult to see what it actually looks like. But if we were able to somehow get outside of our Milky Way and look back, we would see a beautiful spiral structure many, many, many thousands of light years across. In fact, we'd notice a denser spherical region in the center, and we'd notice some beautiful spiral arms if we were looking at our galaxy from above. But if we were then to change our position and look at our galaxy from the side a little bit more, we'd notice the Milky Way has a flattened disk to it. And so we're going to talk about the different structures within the Milky Way. That central spherical region we call the bulge. That flattened disk we call the disk. And yet we also have a much more extended, very low density region called the halo of stars around the Milky Way, in which stars are relatively scarce. You'll notice in our diagram that the sun is not at the center of the Milky Way. We've determined that. And we also notice that we have globular star clusters, which we introduced in a previous lecture, and we'll be back to discuss those a little bit more. Well, all these many, many billions of stars, each with their own gravity, are orbiting around the center of the Milky Way due to the combined effects of their gravity. Now, the stars in the halo tend to orbit in roughly inclined orbits in many different directions, whereas the stars in our disk tend to stay in the disk as they orbit in a flattened distribution. And so we essentially have two distinct populations of stars here, and we're going to see part of the reason for that in just a few minutes. We can get an idea of the sun's orbit by measuring its position and its motion over time with respect to other stars. And when we do that, we find out that the sun has an enormous orbit around the center of the Milky Way. In fact, we estimate it takes well over 200 million years for the sun to orbit once around the Milky Way. What a vast orbit and an enormous amount of time. Astronomers can go another step further by taking the time that it takes to orbit around the center and also the distance from the center that we're able to determine in various ways. We can actually get a good estimate of the amount of mass within the sun's orbit, which typically is appearing at least to be most of the Milky Way. And this number is indeed astronomical. Probably 100 to 200 billion solar masses of material in our Milky Way, perhaps more, as we'll see in a few minutes. Well, in our previous lecture we mentioned that the Milky Way also contains star clusters. We saw the open star clusters. These inhabit the disk of the Milky Way. They may have hundreds, perhaps thousands of stars. They're formed together, as we'll see in a few minutes. And here they may have certain ages, maybe only a few million years old if they're relatively young star clusters, to perhaps some tens of millions or perhaps even hundreds of millions of years old, but not nearly as old as the galaxy itself. On the other hand, we've mentioned outside the Milky Way galaxy are the globular star clusters. Here we have much denser, richer, spherical objects, perhaps hundreds of thousands of stars, and these again orbit outside the Milky Way. Now we notice a very distinctive difference between the types of stars in these two clusters. Our open star clusters tend to have hotter, more massive, bluer stars, whereas our globular star clusters, they tend to have cooler, yellower, and lower mass stars. So based on our discussions of the life cycles of the stars, you might see that this indicates a relative difference in their ages. As we said, the open star clusters may be tens, hundreds of millions of years of age, but our globular star clusters, they can be billions of years in age, some as old as the Milky Way itself. So we see a very distinct difference here, and it tells us that obviously the globular star clusters formed early in the history of the Milky Way, whereas the open star clusters formed later and continue to form to this day. Now, in our previous lecture, we discussed the, again, life cycles of the stars, how they fuse hydrogen into helium in their cores and are on the main sequence of our HR diagram. Well, we really discussed individual stars there, didn't we? Now in this lecture, we're going to step back and we're going to look at the Milky Way as a whole. We're going to look at not single individual stars so much, but millions, even billions of them, and how they interact with each other. So let's do exactly that. Let's look at the life cycles of stars in vast numbers within the Milky Way. And essentially what we're going to see is what we described, but on a much vaster scale. In other words, we're going to see clouds of gas and dust that gradually form stars. Those stars will live through their life cycles and then change and give back material to the interstellar medium. So again, you'll recall that out in space we see these enormous clouds, and in some regions gravity is able to pull them into a denser concentration. Here's where star formation occurs. These areas are denser and colder than other areas, and we can look out into space and image these areas and see different stages of the formation. Often we'll see some regions where the material is particularly dense, and we'll see very young stars. Well, these stars, again, go through their life cycle, converting hydrogen into helium while they're on the main sequence. But then we saw, of course, when they run out of that fuel, they change, don't they? First our high mass stars, and then our low mass stars. And so at some point, our high mass stars, of course, in doing their fusion, generate heavy elements, don't they, beyond helium. These explode violently as supernova, whereas our low mass stars, they move through their life cycle and generate helium and some carbon, and then at the end of their life cycle there in the main sequence, they more gently expel a planetary nebula, you may recall. But both types of stars essentially are expelling matter back out into space, and here's a key point, enriched with heavier elements. So each succeeding generation of stars essentially cooks up or fuses heavier elements, and when it returns material back out into the interstellar medium, now the interstellar medium will gradually be enriched in these heavier elements. Well, that material, of course, will eventually cool down. Gravity will again go to work and pull that material into denser regions, and the process can start all over again. And so we would expect to see perhaps multiple generations of stars in the Milky Way. Some very, very old, others not nearly so old, and perhaps others very young, even forming today. And therefore we can piece together the entire cycle. So let's just go ahead and summarize that very briefly. Again, gravity forming new stars in those clouds. Those stars fuse heavier elements by fusion, and then whether they be lower mass or higher mass stars, they're going to expel that material back out into space with additional heavy elements that enrich the interstellar medium. That material will expand and cool down. Gravity will eventually again contract it to form the next generation of stars. So stepping back and looking at the Milky Way as a whole, again, we would expect to see this process occurring, and we're going to find out that it really occurs in the disk. It really occurs in the disk. How do we know that? Well, first of all, we noticed on our earlier diagrams that the central region, that bulge, was composed mostly of older, lower mass, cooler stars, whereas our disk was composed more prominently of younger, hotter, more massive stars. And there already we have one clue that that's where the star formation is occurring, don't we? Well, from our vantage point, as we look out into different regions of the Milky Way, we do see these clouds of gas and dust forming stars. These are called emission nebulae because the fact that they emit light of various wavelengths, and they're a nebula or a cloud of gas and dust. Now, interestingly, they give off usually a very distinctive type of light or distinctive color, Often when we take a picture, we'll see a very beautiful glow of red. Why red light? Well, this is the wavelength of hydrogen. When hydrogen is excited by energy, it will in turn give off red light. So for our purposes, we can look for those areas where we might see clouds of red light, and we would know that there would be star formation going on there. You may be familiar with the very famous Orion Nebula, a well-known nebula that has that distinctive red color. So throughout our Milky Way, again, we would see these patches, these nebulae, and we'd say there's where the star formation is occurring. We can actually get confirmation of that as we look out at other galaxies. We'll see in our next lecture. Here we may see again something very similar to the Milky Way, a spiral galaxy, and we would be able to pinpoint these regions of hydrogen where stars are forming. In other areas, we may be able to notice fairly young star clusters. How would we know they're young? Well, again, by the presence of hot, massive stars, which we know don't last very long on the main sequence, do they? So if we do see a cluster with hot blue stars, we know they can't be very old and they needed to have formed fairly recently. In other ways, we can even detect these clouds at other wavelengths of light other than the red light we mentioned, and again be able to isolate them and know that at some point in time they may as well form stars. So this gives us a pretty good idea why we see these beautiful spiral arms, not only in the Milky Way galaxy, but in others. But let me just emphasize briefly that these spiral arms are not solid objects. No, here is where we just have an increased density of stars and gas and dust. Other areas may not have nearly as much, and so these are just simply more prominent. But evidently these are very long-lived features, because as we look out of the Milky Way at other galaxies, we see many, many spirals showing these distinctive structures. So we've got a pretty good idea now of some of the things that are occurring in the Milky Way, and we can go back and take a fresh look now at our Milky Way, and again, see that central bulge, older, cooler, lower mass stars, in contrast with our disk, which is made of hotter, younger, more massive stars. We now have a good idea where the star formation is in the disk, in those emission nebulae. We saw that the sun is not necessarily at the center of the Milky Way, but quite a distance out. We saw too this very low density or halo of stars around the Milky Way. And finally, we touched on those globular star clusters outside the Milky Way, whereas we have the open star clusters within the Milky Way. So already we've established a very nice picture of our Milky Way that we can keep in mind going forward. Can we get any idea how the Milky Way formed? Why is it the structure that it is? Well, these are obviously enormous structures, galaxies, the Milky Way no exception, but we can paint a very simple picture. We won't go into great detail as it is quite a complex topic. But let's go back in time, billions of years, early in the universe. We can't imagine the universe being perfectly uniform in density. Instead, we would certainly expect there to be areas that are a little more dense or a little less dense. And once again, as we've seen many times, gravity is going to work on these areas. It's going to slowly contract these regions of higher density, and these will eventually turn into galaxies. Now, interestingly, gravity would take time to do this, and before it's able to contract the galaxy significantly, star formation can actually begin. So picture now a roughly spherical cloud early in the history of the universe, and as gravity slowly begins to contract it, star formation can begin. Well, you know that the objects here would be randomly scattered throughout this cloud. Some would be quite far away, and they would be orbiting at a very slow rate. Even as the cloud contracts, they would maintain that very slow orbit, and these orbits would be in many different inclinations. Yes, it's exactly what we described earlier. This would be forming the halo of our galaxy, a very low density region. As the rest of the cloud contracts, these halo stars would remain in these early orbits. Well, as the cloud contracts, gravity is bringing it closer together. The cloud is going to begin to spin due to conservation of angular momentum. And as a result of that spin, our cloud is going to begin to flatten. Yes, it's going to flatten into that disk that you and I see today. Now, most of that material in our early galaxy is going to, of course, end up in that disk. It's going to be a higher density. We still have that very low density halo. Much of that material will end up in the center, and that early generation of stars, again, that we see today as the bulge. But much of the raw material, so to speak, of our galaxy remains in the disk as it flattens and spins into what you and I see today as the Milky Way. Well, if there's raw material in the disk, again, we can understand that there would be successive generations of stars forming, living, and dying in the disk over vast periods of time, and at some point our sun would form as one of those generations of stars. We saw in an earlier lecture approximately 4.6 billion years ago. One final piece we'll see in a future lecture is that as this enormous young galaxy is forming in the early universe, there were numerous galaxies, some not nearly so large as the Milky Way, and therefore over time the Milky Way would actually draw these in and absorb these other galaxies. So we'll see that this is a significant component to the Milky Way as well. Well, is there any way we could know perhaps of an interesting location in the Milky Way, say the center of the Milky Way? Would there be anything special happening there? We painted this picture of this bulge of ancient stars. They all have their various orbits, but what about the center? Well, unfortunately, we can't simply look at the center with telescopes in visible light. Why is that? Well, we've said several times that there is gas and dust within the disk where we live, and we simply can't see through it. So astronomers have had to employ some other means to be able to look into the center. And it turns out that by using telescopes at other wavelengths, we can see through that dust and get an image, get a view of the center of the Milky Way. Now you recall we said the sun is quite a distance from the center, 28,000 light years away. And yet with some of our more recent technology, we're able to get a clear picture of what's going on there. So let's go ahead and progressively zoom in. At first we may take a standard picture and see a few stars in the direction of the center. And as we zoom in a little closer, we may be able to notice some different gas clouds and dust clouds in our way. But if we go ahead and employ, again, other wavelengths of light, we can look through that material and we begin to notice some very interesting structure at the center. Zooming in either further, we're going to see, of course, a number of stars there, greatly compressed in the center. And here is where there was a major discovery in recent years. We might expect these stars to be randomly orbiting, perhaps even chaotically, and yet what was found was that a fair number of them are orbiting something extremely massive. How do we know that? Well, we know that because of their motions. These stars are orbiting something very massive because they are moving very, very quickly. And if we were to carefully measure their orbits, as we described in a previous lecture, the period for their orbits and the average distance of their orbits from the center, we could, in a sense, use their orbits to probe that massive object, much as we discussed how we know the masses of stars. Well, one team in particular at UCLA did get the clearest possible view of the center with our most recent technology. They measured the positions of a number of stars and made an astonishing discovery. What they found at the center of the Milky Way had approximately the mass of 4 million times that of our sun. And yet, this object gave off virtually no light. Well, I think from our previous discussions, you can probably guess this is a black hole. And this is not just a black hole that we might see formed from a single star, but it's what astronomers now call a supermassive black hole. Again, almost 4 million times the mass of our sun. This is an enormous black hole by the standards that we've discussed, and yet these stars are zipping around it at extremely high velocities, due to its powerful, powerful gravity. So this was a major discovery. Now we don't need to imagine that everything orbits the black hole in the galaxy. No, we said that there's billions of stars, and it's really an incredibly complex situation here, the combined net gravity of all the stars. But there at the center, that black hole certainly does dominate the center of the Milky Way. So we've painted quite a picture, haven't we, of our home galaxy, the Milky Way. We've gotten acquainted with it as a spiral, and it's time for us to review the things we've discussed. We saw that there's a disk of stars and gas around the center of our Milky Way. The center comprised of that bulge of stars, and then we have this very low density halo of stars. We noticed a very distinct difference, though, didn't we, in the populations of stars? We said that the central bulge and the halo, once again, tended to be older, lower mass, cooler stars, whereas in our disk we saw far more of the younger, hotter, higher mass stars. That was our first clue, wasn't it? That star formation is occurring in the disk, not so much in the bulge. We saw that, again, the disk stars orbit in the plane of the disk, whereas the bulge and halo stars tend to orbit at random inclinations. And we actually saw the reason for that, didn't we? We saw somewhat of a relic or fingerprint, so to speak, of the formation of our galaxy. Those bulge and halo stars formed earlier in those randomly inclined orbits and have remained there ever since, whereas the disk stars formed after the Milky Way flattened into a disk. We then looked at the stellar life cycles in the disk. Stars form from clouds of gas and dust. They live through their life cycles, forming heavy elements that are then expelled back out into space to form the next succeeding generation of stars, which therefore are slightly enriched in heavier elements. And we saw the areas where that's done, didn't we? Those emission nebulae, those clouds of gas and dust, where we saw that very distinctive reddish color of hydrogen gas forming stars. Finally, we again looked at the formation of the Milky Way, how it contracted under gravity, forming that bulge, halo, and disk. And we finished with an astonishing discovery of a supermassive black hole, 4 million times the mass of our sun, at the center of the Milky Way. So really quite an amazing picture that modern astronomy has been able to provide us of our Milky Way. What was once simply a band of light in the sky has been transformed into a majestic structure of great complexity and great interest to us. And the Milky Way, being our galaxy, then provides us a model with which we can go out and look at other galaxies and compare them to them. So those other galaxies will be the subject of our next lecture.